And now, can we use Carnot cycle to make the most ideal refrigerator or the most ideal heat pump? And what do you think? Again, we discussed Carnot cycle for heat engine. So many times we use Carnot engine, which is the most ideal heat engine that we can ever think of. Same way, we could use the Carnot cycle to make the most ideal refrigerator and heat pump. And how can we possibly make it happen? So now, let me draw a test diagram again. Okay, for Carnot heat engine, we draw this rectangle, okay, FTH here and TL here, and also we have S1 and S2. And for Carnot heat engine, we start from here and move like clockwise. Okay. And now, as we discussed earlier in the previous lecture, when you try to make the refrigerator and heat pump, we basically have to reverse heat engine processes. So what it means is that in TS diagram, in order to make a Carnot refrigerator or Carnot heat pump, we have to reverse all entire process. So instead of this direction, we should turn that back to make a reverse process like here, 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 here. So now, again, that in the case, it should be counterclockwise. Then now, let me just try to start from 1, 2, 2, 2, 2, 3, 3 to 4, and 4 to 1. So that is for Carnot refrigerator or Carnot heat pump. Now, from 1 to 2, at low temperature, we are going through reversible heat input process. Okay? And from this 1 to 2, we take heat, QL, from certain space we need to cool down. Okay? Now, from 2 to 3, that is isentropic compression process. And now 3 to 4, that is at high temperature, isothermal heat rejection process to where? To your kind of warm surroundings. Okay? It could be your kitchen area. It could be, outside your house when you try to turn on Carnot air conditioner. And now from 4 to 1, that is again the expansion process, which is isentropic process. Okay, so that is how can you draw TS diagram for Carnot refrigerator and Carnot heat pump. Then, how can we calculate the COP? Okay, so do you remember the COP definition of a COP for refrigerator and heat pump? So, okay, let me just draw it. Erase it. Now, COP for refrigerator can be expressed as QL, the desired output divided by required input, which means W net in, or we can say that is QH minus QL. Okay. Now, for heat pump, that is QH divided by QH minus QL. Now, if you try to apply that equations to Carnot cycle, we already know that QL can be expressed as TL S2 minus S1. QH is TH times S2 minus S1. And QL is TL times S2 minus S1. So by putting those equations together in the definition equation of COP, we find those whole common terms. So what do we have? What we have is now COP can be expressed in terms of TL divided by TH minus TL. So that is the COP of refrigerator when we think about Carnot cycle or REV. So either way, you can use C or REV. Okay. Now, with the same procedure, the COP of the heat pump, when this heat pump is made of Carnot cycle, then COP can be written as TH divided by TH minus TL. Okay, then that is reversible. Obviously, by looking at these two equations, always TH is higher than TL. So same thing as we discussed earlier in the previous lecture, always the COP of heat pump, even for Carnot cycle, is greater than COP of the refrigeration. So, okay, and obviously we can see that COP, that is COP of the refrigerator plus 1.
Now let's think about two reservoirs again to understand the Carnot refrigerators. So one reservoir is warm environment at temperature 300 Kelvin, and the other reservoir is cool refrigerated space that should be maintained at temperature 275 Kelvin. And now we want to design a refrigerator that runs under those conditions. Then what would be the maximum, the best COP of the refrigerator that we can possibly make? In the case, the COP for the reservoir, refrigerator, is for the Carnot cycle. In the case, we can calculate that as TL divided by TH minus TL. And by using those numbers that are given, 300 Kelvin and 275 Kelvin, the COP of the Carnot refrigerator gives us 11. Okay. Just in case, if we use the same Carnot cycle as heat pump, not the refrigerator, then we can calculate this COP using this equation that gives us 12. But that is not important at this moment. Now, so this COP is the best and maximum COP that we can achieve. Then let's try to think about two cases. One is, this refrigerator, and the COP of this refrigerator is 7. Now, can you make it? And answer is yes, because this COP is smaller than the Carnot COP. Okay? And the reason why we have smaller COP of this refrigerator than the Carnot case is because we have many irreversibility. Okay. Now, how about another refrigerator, and this COP is 13? Can we make it, possibly? And answer is no, it's not possible, because COP for this case is higher than COP of the Carnot cycle. So then this condition cannot be made.